Hello everyone, welcome back to my YouTube channel. My name is Ray, and in today's video we're going to be looking at the asymptotic behaviors of rational functions, specifically vertical asymptotes and removable discontinuities. I wanted to start off by explaining what a vertical asymptote is. So a vertical asymptote happens when the function grows and grows without bound near a specific x value. So if we take a look at this example that I drew here, right, we have our vertical asymptote, which is equal to x equals 1, and our horizontal asymptote, which is y equals 0. In this video, we're going to focus on this only, right? So here we have a function, and this function is approaching x equals 1, right? It's getting closer and closer to x equals 1, but it's not touching it. Instead, the y is going up, 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 towards positive infinity. Now let's take a look at this side of the function. Again, it's approaching x equals 1. It's not ever going to touch it, right? Because there is no limit. But it's going to go down, 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 down to negative infinity. So, in other words, as x gets closer and closer to some number, the y values will either get bigger, 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 or smaller, smaller, smaller without limit. So now let's go ahead and look at this example with vertical asymptotes. So the first thing that you have to do when you get this problem is factor out the numerator and the denominator. So this numerator is different though because it cannot be factored. It's already in its simplest form, so all we're going to do is just carry it down and keep it as is. The reason we can't factor it is because there's no greatest common factors that we can pull out and no other way to factor it, right? It's in its simplest form. But we can factor out the denominator. And at first when you look at it, it looks strange because it's written in reverse, right? Typically, you have your x squared in the front, now you have it in the back. But if you rewrite this, this is the same as negative x squared, because this is negative right here, minus x, again, this is negative, and then plus 2. Why plus 2? Because there's no negatives in front of the 2. Perfect. Now you need to factor this. And again, if you have not watched my factoring video, please go ahead and watch it. It's going to make factoring so much easier for you. So let's go ahead and factor this. One thing I noticed is that we can pull out the negative sign from the expression because I do not want my x squared to be negative. So what I'm going to do is I'm going to take out the negative sign outside of my parentheses. So it's going to be negative x squared plus x minus 2. Perfect, I have that set. Now what do I have to do? Well, I need to find something that adds to get me 1, but then multiplies to get me negative 2. That's going to be x plus 2 times x minus 1. Why 2 and negative 1? Well, because 2 times negative 1 is negative 2, and 2 minus 1 is positive 1. And we always need to bring down that negative sign. We can't get rid of it. So now we have our denominator factored, right? We can set up our expression as it used to be. 5 plus 2x squared over negative x plus 2 times x minus 1. Okay, we cannot cancel anything from our numerator and our denominator. That would be a removable discontinuity, and I'm going to go over that next. So this means that these two down here are going to be our vertical asymptotes. We need to set them equal to 0 though. So x plus 2 is equal to 0. X minus 1 is equal to 0. X is going to be negative 2. X is going to be 1. We have two vertical asymptotes, one at x minus 2 and one at x equals 1, right? So that is how you find the vertical asymptotes when given rational functions. All right, so now let's talk about removable discontinuities. So first let's start by discussing what continuity means, right? A function is continuous if you can draw it without lifting your pencil. Therefore, a discontinuity would be a break in this continuous graph. It means that your function will no longer be continuous at a certain value of x. There are several types of discontinuities, such as holes or removable discontinuities, vertical asymptotes, and jumps. In this video, we're going to be focusing on removable discontinuities only, but there will be another video about those other types. So the first thing that we have to do is take this rational function and factor the numerator and the denominator. So the denominator can be factored through difference of squares, right? This is the same as x plus 1 times x minus 1. Great. Now let's factor the denominator. We need to find something that adds to -2, but that multiplies to -3. That's the same as x minus 3 times x plus 1, because -3 times 1 is -3, but -3 plus 1 is -2. If for some reason you did not understand how I factored the denominator and numerator, please go and watch my video series on how to factor. Right, so now we factored the numerator and the denominator. What do we do next? Well, we need to note discontinuities and vertical asymptotes. A discontinuity exists when you can cancel out a factor in your numerator and a factor in your denominator. If we take a look at our denominator, we have x plus 1 times x minus 1, and then our denominator is x minus 3 times x plus 1. X plus 1 and x plus 1 are the same. They can be canceled. So if we cancel it, we know that at x plus 1 equals 0, or at x equals -1, we have a hole, or a removable discontinuity, right? So whenever we cancel, then between numerator and denominator, there's going to be a removable discontinuity. But we have x minus 3 left over. If we remember from the work we did here in vertical asymptotes, everything that was in the denominator, if it wasn't canceled out with anything in the numerator, was considered to be a vertical asymptote. So x minus 3 equals 0, or x equals 3, is a vertical asymptote. This can be rewritten as x minus 1 over x minus 3. And we keep in mind that there is a hole, or a removable discontinuity, at x equals -1, and a vertical asymptote at x equals 3. So to summarize, removable discontinuities happen whenever you factor out your numerator and your denominator, and you get a factor that's the same in the numerator and in the denominator, and that can be canceled out. So the reason we were able to cancel out x plus 1 on here and down here was because they are the same, right? And whatever's canceled out is considered a hole, or a removable discontinuity. Whatever's left over and cannot be canceled out is considered a vertical asymptote, right? We can't cancel out x minus 3 because there is no x minus 3 up here. If there were an x minus 3 and we would be able to cancel it, then that would no longer be considered a vertical asymptote. It'd be considered a hole. So again, memorize this. When you can cancel from the numerator and the denominator, that's a hole. If it cannot be canceled out, it's a vertical asymptote. All right, I hope that you guys understood this video. Please like and subscribe, and if you have any further questions, please leave them in the comments. I'm here to help you, and I'm here to make videos to help you understand math, chemistry, and any other science as much as possible. Thank you for watching, and I'll see you next time.